Okay,
Should-
welcome again to the European and Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Łukasz Kubat from the University of Warsaw. The title of his talk is on Yang-Baxter algebras. Please.
Thank you, Salvatore. So I would like to thank you for the invitation, for the opportunity to give this talk, and then I can focus on my talk, and it will be, as in the title, on the Yang-Baxter algebras. But before I proceed to the definition, what is Yang-Baxter algebra, I will try to give you some motivations for considering such structures. Oops, I cannot, oh, I see. So what are I will try to give you some background and say what are the main characters of my talk. So the situation is as follows. We consider the free algebra of non-commutative polynomials on a set X. And as we know, each algebra over a field F is a quotient of such a free algebra. And if we have a quotient of the free algebra by an ideal I, then this quotient is said to be finitely presented if both the set of generators X is finite and the corresponding ideal is finitely generated as an ideal. There is also a second type of algebras we will be considering here, and these are called quadratic algebras, and this is exactly the case in which our ideal I is generated by homogeneous polynomials of degree 2. And among quadratic algebras, there is a family of algebras defined by maps. So here we are in a very special situation. We start from a map defined on a Cartesian square of the set X, and then we define our ideal of relations that it's generated by differences of words of length 2, xy minus uv, provided uv is the image of xy under the map R. And having such a map, we say that the corresponding algebra, so the quotient of the free algebra by the corresponding ideal, we call such a map the structure map of the structure algebra of the map R, or the structure algebra of the pair X R. So clearly this algebra is not only quadratic, but it's also a monoid algebra, because if we define a monoid M having X as a set of generators and relations of the same form as generators of the ideal I, then it's clear that our structure algebra is exactly the monoid algebra of the monoid M. So in particular, if the set X is finite, then our structure algebra is finitely presented, because X is finite and the set of words of length 2 generating our ideal is also finite. And our algebra is also quadratic and monoid algebra, okay? And we will be focused on that class of algebras. So why one should consider such algebras? One natural answer to this question, I have some question on the chat. Oh, I assume everything is fine. So one motivation is that such algebras lead to structures with very, very nice algebraic, homological, combinatorial, and so on properties. And the second motivation is that such algebras also appear in various branches of mathematics and also mathematical physics. Just to enumerate some of them, these are such algebras clearly appear in general non-commutative ring theory. In some parts of non-commutative algebraic geometry, for example, as deformations of certain classical algebras. They also appear in quantum groups and Hopf algebras, in topology, as cohomological algebras of KP1 spaces, also in number theory, via K-theory of rings of fields, and as I said before, in some parts of mathematical physics. Okay. And these algebras are also interesting because with them there are still many important but unsolved in the full generality questions. For example, there are some questions corresponding to arithmetics of such algebras or the structure of prime ideals in such algebras. Among them, there is always a question about the minimal primes because they somehow determine the structure of the algebra. There are also questions related to nil and nilpotency conditions, and among them, there are two very famous. One of them is related to a mitzvah and asks whether the Jacobson radical of such an algebra is locally nilpotent. Or there are also questions when the nil condition, which means that each element in such an algebra is nilpotent, when such nil condition implies that the whole algebra is nilpotent. And positive answers to these questions are known, for example, from a long time for commutative algebras, but also in a bit more general context for algebras satisfying non-trivial polynomial identities. But in general, even if we restrict to very special subclasses of finitely presented algebras defined by homogeneous semigroup relations, which means that these are semigroup algebras in which the relations are of the type that one word of the fixed length is equal to another word of the fixed length, that even if we restrict to such classes of algebras, the answers to the problems I mentioned and some other important questions are not known in general. So the conclusion is that if we have some natural class of algebras, that partial results even for this class are important. So before I will give you a definition what a solution of Yang-Baxter is, I can state a general aim, which can be read as follows. So having a map R on a set X, we can try to find a link between combinatorial properties of our map R and algebraic properties of related structures associated to our pair to our map R. So the aim is how to translate the combinatorics of the map R into algebraic properties of associated structures and vice versa. How knowing some algebraic properties of associated structures, what can be said about our original map. And it turns out that this question is particularly interesting if our map is not arbitrary, but if it satisfies some extra properties. And later I will try to explain you how Yang-Baxter equation appeared. But before I will explain you, I will give you a definition. So a solution of a Yang-Baxter equation is a map defined on a Cartesian square of a set, coming from this Cartesian square to itself, and satisfying the following braid relations, which R12 composed with R23, and again R12 is equal R23, 1, 2, and 2, 3, where R12 simply denotes the maps from Cartesian cube of X to itself, and acts as R on the first two components and as an identity on the remaining component, and similarly R23 acts as an identity on the first component and as a map R on the remaining two components 2 and 3. So having a solution of the Yang-Baxter equation, so not a general map R, but a solution, then we call our structure algebra just the Yang-Baxter algebra. So if you prefer to look at the Yang-Baxter graphically, then the Yang-Baxter corresponds exactly to such a node picture, which is For example, in topology or in knot theory, this is known as the Rademacher third move. So actually, Yang-Baxter equation appears each time we have something to do with the braid relation, which appear in many various parts of algebra and in general in mathematics. So to go further, we need some notation. So having a map on Cartesian square of X, we need a notation for its components. So the left component will be denoted by lambda X acting on Y, and the right component will be denoted with the use of a row. And here are some conditions, some extra conditions that we put on our solution. And if, for example, the set on which our solution is defined is finite, then we call our solution finite. If the map is bijective, then our solution is called bijective. If the map is involutive, idempotent, or has some other properties, then we respectively say that our solution is involutive, idempotent, and so on. And there is also one more natural condition that will allow us to work with permutation groups is the following, the condition of non-degeneracy. For example, if all the lambdas, so left components of our map are bijective, then we say that our solution is left non-degenerate. And similarly, if rows are bijective, then our solution is right non-degenerate. And if it's both right and left non-degenerate, then it's simply called non-degenerate. So up to now, we have objects, solutions of the Yang-Baxter equation, and you can easily imagine that it's also possible to define maps between solutions, so simply morphisms of solutions. So having the notion of morphism, actually we get a category of solutions of the Yang-Baxter equation, and having a category, now we can think about objects up to isomorphism. And the more natural problem as in general in mathematics is to try to construct objects and try to classify them up to isomorphisms. And these problems was posed in, I think, in 1992, not exactly 90, by Drinfeld at some conference devoted to quantum groups. So this is what Yang-Baxter equation is. And as I mentioned before, it appears in many contexts. So here I have some examples of solutions. So let's start from the following. Having two maps on a set X, if we define the map R in the following way, that the left component is lambda, look at lambda and rho, they do not depend on sub-indices, then this formula gives you a solution if and only if the maps commute. And this solution is bijective clearly if and only if the lambda and rho are permutations. And it's also easy to say when such a solution is left or right not degenerate. And that was defined for a bare set X without any extra structure. What happens if we have some extra structures on a set X? For example, if we have just one binary operation on a set X, then it can be checked that such a formula x, y goes to y, comma, y, circle x, gives you a solution, if and only if this binary operation is self-distributive, less self-distributive in the following sense. And set with a binary operation, which is a self-distributive, is known as a rack. And such a structure appears very frequently in topology, especially in knot theory. For example, if you start, if X is a group and circle is just a conjugation in a group, then you again obtain a rack. So again, a solution of the Yang-Baxter equation. But there are also solutions related to algebraic structures with more than one operation. And for example, having a ring, actually you have to assume that this is a Jacobson radical ring. For example, nilpotent ring is an example of a Jacobson radical ring. Then there is a this time maybe a more involved formula, but again, starting from a ring, Jacobson radical ring, we can define a solution of the Yang-Baxter equation, which is involutive and non-degenerate in that case. Also, lattices produce solutions, but in this case, having a lattice, if we take a mid and join and mid on the left and right component, then we again obtain a solution, but this time the solution is idempotent. This is, of course, related to the fact that the operations in a lattice are idempotent. There is a question to which properties are these? What are the corresponding algebras properties? I will answer this question a bit later. Okay. So here are 4 examples of solutions. So as you see, solutions can be associated to various algebraic structure. And what type of questions may we ask? Of course, having a solution and the corresponding algebra, we can ask about many ring theoretical or homological properties, but in this talk, I will try to focus on the following. So I will try to tell you something about the Noetherian condition, about primeness and semi-primeness, about when such algebras satisfy polynomial identities and when such algebras can be embedded in matrices algebras. I will give you some information about classical dimensions for algebras, what are the dimensions in this case. And then, having enough time, I will try to say something about homological regularity of such algebras. So the general question is what type of results we can expect. And before we proceed to Yang-Baxter algebras, I will try to sketch you some classical results which are known. So just recall that an algebra over a field is called Pi, provided there exists a non-zero polynomial in general in non-commuting variables, such that evaluation of this polynomial at arbitrary elements of our algebra vanishes. And in 60s and 70s of the previous century, it was shown that having a semigroup which is cancellative, then the semigroup algebra of this semigroup satisfies a non-trivial polynomial identity if and only if the semigroup has a group of fractions such that the corresponding group algebra is Pi, which is also equivalent that S has a group of fractions which is abelian by finite in case the characteristic is 0. And if we want to have Pi algebra, G must be P abelian by finite if the characteristic of the base field is positive. By P abelian, I mean that the derived subgroup of our group is a finite P group. So there are some theorems characterizing when at least some semigroups leads to Pi algebras. But also in this case, it's known that the corresponding semigroup algebra is semi-prime if and only if the semigroup, the group algebra of the group of fractions of S is semi-prime. And this always happens in characteristic 0, and it happens in positive characteristic if and only if the torsion part of the finite conjugation center is a P-prime group. Among other classical results concerning finiteness condition for semigroup algebras, there is a result of Zelmanov from late 70s, which describes when semigroup algebras are Artinian. So this happens let's focus on the level of monoids. This happens exactly when the monoid is finite. So looking at our Yang-Baxter algebras, because in our case, the structure monoid is never finite. So our algebras, Yang-Baxter algebras are never Artinian. So the natural question is to ask when such algebras are Noetherian. We can pose even a more general problem for monoid algebras when monoid algebras of arbitrary monoids are left or right Noetherian. And as you know, this is an open problem even for group algebras. What is known, there is also a bunch of classical results that a group algebra is left Noetherian even only if it's right Noetherian, because on KG we have a natural involution determined by the natural involution in G, which is an inversion of an element. So Noetherianity for group algebras is a symmetric property. And all we know is that group algebras of polycyclic bifinite groups are Noetherian. There is a conjecture that the converse also holds, but up to now, nobody knows whether it's true. Later in the 70s and 80s, Farkas, Schneider, Cleave, Brown, Jespers, Smith, and some other authors proved that if additionally G is torsion-free and polycyclic bifinite, then KG is not only a Noetherian algebra, but it's also a domain. And it's also possible to characterize in terms of the torsion part of the finite conjugancy center when such group algebras are prime. The answer is also no for certain very special types of monoids. And this is a result of Jespers and Okniński from 2006, that having a monoid, but which is a submonoid of a polycyclic bifinite group, so it, in particular, M sits in a group, which means that M is cancellative, then the corresponding monoid algebra of this monoid is one-sided Noetherian, if and only if M satisfies the ascending condition on the one-sided ideals. And this is also equivalent that M has a group of fractions, and this group of fractions have a subgroup of finite index in G with a derived subgroup sitting in the monoid, and such that the intersection of this subgroup with M is finitely generated. Moreover, in this case, as you see, the problem of left and right Noetherianity is equivalent. So there is a left-right symmetry for such monoids sitting in polycyclic bifinite groups. But in general, not a lot more is known. Okay, now let us say something about representability. So an algebra over a field is called representable if it can be embedded in a finite matrix algebra over some field. This field must be a field extension of the base field. In general, it can be huge, but what is important is that such a field exists. And such a knowledge that our algebra can be embedded in a matrix ring is very useful, because for matrix rings we have some extra tools. For example, if we look at matrices not as an algebra but as a semigroup, there is a whole machinery of linear semigroup that can be applied in this case. So knowing that we deal with representable algebras is some extra information. And there is a classical result from the 80s attributed to Ananin, which says that if you have a PI algebra that is one-sided Noetherian and finitely generated, then such an algebra is always representable. The next result says something about the dimension of the semigroup algebra. So in that case, in 80s, Gromov and Grigorchuk proved that having a cancellative semigroup, the Gelfand-Kirillov dimension of such algebra is finite, if and only if our semigroup has a group of fractions and GK dimension of this group algebra is finite. And this is also equivalent that the group of fractions is nilpotent bifinite. And in that case, the GK dimensions of the group algebra and semi-group algebra are equal. And there is also a formula for this dimension. Okay. And I need another definition, but with this definition, I will try to convince you that among all maps defined on a Cartesian square of a set X, the solutions of the Yang-Baxter equation play a very special role because they lead to special algebras. But the definition is as follows. So in the late 90s, Gateva, Ivanova, Vandenberg, and also other authors, Ettinghoff, Schedler, and Soloviev among them, they investigated monoids of a very special type. These are the so-called monoids of I-type. And the idea is as follows. Words in our monoid are in a bijection with words in a finitely generated 3 abelian monoid, but the bijection is special. If you choose one word of our monoid M, say V of A, and if you multiply this word from the left by all possible generators, then these words can be recovered from the word A in the 3 abelian monoid. You multiply this word by generators U1 up to UN, and then apply a bijection V. So the words on the left, on the set on the right, are a permutation of the words that appear on the set on the left. And because of this, if you fix A, or if you take as A generator from X, this will give you a map between X square and X square. So having such a monoid of I-type, there is automatically associated a map from X square to X square. And Gateva, Ivanova, and Vandenberg characterized monoids of I-type in the following way, that having a monoid M with such a presentation as before, this monoid is of I-type if and only if the associated to this monoid map R is a non-degenerate and involutive solution of the Yang-Baxter equation. So somehow solutions with nice properties naturally appear in the investigation of such monoids. And later, monoids of I-type were described also as regular submonoids of 3 abelian of the semi-direct products of 3 abelian monoids with with symmetric groups. So in particular, it was shown that if you look at this monoid or its group of fractions, which has a similar presentation as the monoid, then the group we obtain is torsion-free abelian by finite. So it's a Bieberbach group, which means it's a group that appears in geometry very frequently. So Gateva, Ivanova, and Vandenberg also showed some ring theoretical properties for algebras related to monoids of I-type, or as I said before, this is equivalent to saying something about Yang-Baxter algebras of involutive non-degenerate solutions. And they prove that such algebras are always two-sided Noetherian. They are always domain, and they are always PI, so satisfy non-trivial polynomial identities. So because such an algebra is domain, it's Noetherian, so it has a ring of fraction, which is a division ring, and moreover, A is a maximal order in such a ring of fractions. And this algebra is also homologically regular. I don't want to go into details, but it can be shown that it's always Kosul, Cohen-Macaulay. It has a finite global dimension, which is a part of definition of Auslander regularity. Moreover, it's easy to check, relatively easy to check, knowing these 3 points that I just described. that the classical dimensions of this algebra are exactly, I mean the classical Krull dimension and GK dimension are exactly the size of the set of generators X. So the conclusion is that despite these algebras are non-commutative in general, they produce a class of algebras with really nice arithmetical, homological, and structural properties, which are very similar to properties that appears for classical commutative polynomial algebras. And here are some examples what happens if we consider some special solutions. So clearly, if you take an identity, then this is a solution, but what happens in this case? Identity is, of course, an involutive solutions, but if the set X is not a singleton, then this solution is degenerated. What happens at the level of algebra? If you look at the ideal of the definition of this algebra, structure algebra, the ideal is the zero ideal because we don't have non-trivial relations. So the corresponding algebra is the free algebra. So it's never, if X is not a singleton, it's still domain, but it's never Noetherian. There are also some other examples. For example, in this example, built on a set of cardinality free, coming from free transpositions, it's possible to check that such a formula gives you a solution which is not bijective, which is not no longer involutive, but it's of order 3. It's two-sided non-degenerate, and its algebra has the following presentation. It's still Noetherian, still PI, but it's not semi-prime, so it's also not a domain. So if we skip some nice properties of our solution, for example, involutivity or non-degeneracy, also some nice properties of the corresponding algebras are lost. For example, the last example on a set of cardinality 2. So xy is sent to yy. In that way, we obtain an idempotent solution, which is one-sided non-degenerate, left but not right. In that case, we obtain Yang-Baxter algebra, which is still PI, but Noetherian also on one side, on the left side, but not on the right. And it's also not semi-prime. So if we skip bijectivity of our solutions, that also some lack of symmetry in Noetherianity appears. So the conclusion is the following. If we want to investigate algebras with nice properties, I mean algebras coming from solutions of the Yang-Baxter equation, we have to impose some extra conditions on our solutions, because otherwise, as you saw, we may obtain a free algebra or something which is not Noetherian. And it's easy to check that the necessary condition to obtain something which is Noetherian is the assumption that our set X is finite. And because the solution, the identity solution, which is degenerated, leads to free algebra, we should at least assume that we deal with solutions which are one-sided, non-degenerate. Otherwise, a complete mess can appear, and we cannot expect nice properties. So from now, I will focus on finite solutions, not necessarily bijective, but non-degenerate, at least from one side, okay? And in tackling of the Noetherianity problem for such solution, of Noetherianity problem of Yang-Baxter algebras related to such solutions, there is a theorem which is very helpful, which describes the Noetherianity of semigroup of a monoid algebra in terms of some natural properties of the monoid. So having a finitely generated monoid, its semigroup algebra over a field is right Noetherian if and only if the monoid satisfies the ascending chain condition on right ideals. This is, of course, necessary condition. If you want algebra having ACC on right ideals, then the monoids should satisfy such a condition. But also the GK dimension should be finite, so the dimension also should play a role. And moreover, such a monoid should allow a chain of ideals with nice quotients. So among quotients, what can happen? Quotients can be either power nilpotent or a completely zero simple inverse semigroup. If we are able to build such a chain of ideas with quotients with such properties, and if we have a monoid with ACC on right ideas and the corresponding GK dimension of the algebra is finite, then we control the at least one-sided Noetherianity of our algebra. And basing on this theorem, we are able to obtain such characterization, not the full characterization, but at least in some natural cases. But to deal with one-sided Noetherianity of Yang-Baxter algebras, we would like to, because the corresponding algebra or the corresponding to this algebra monoid is too complicated, we need to do some intermediate step. So to a general solution, we associate something which is called the derived solution. If you look at this formula with R prime, so from lambdas and rows, we can build sigmas and obtain a solution of that form. You see at the first component, we have just the identity. So xy is sent to y sigma y of x. And this solution is much simpler in dealing. So associating to such solution its monoid and first investigating this solution and its algebra, we have some intermediate knowledge, and using this knowledge, we can derive something, some information. We can pull some information to at the level of the general solution. So somehow this derived solution controls the behavior of the map R square. And the idea is the following. In 2022, it was proved that having, as I said, finite left non-degenerate solution, then the semigroup algebra of this derived structure monoid or structure monoid of the derived solution, then the algebra is always left Noetherian PI and of GK dimension not exceeding the size of X. So it's in particular, it's finite. And now there is a trick which allows to connect the information about the algebra Ka and the algebra K of M, which M means the structure monoid of our original solution. And the trick is the following, that there is a bijective one cocycle. First, there is a, there is an action of the monoid M on the monoid A via automorphism, and there is a bijective one cocycle with respect to this action. And this allows us to realize our monoid M as a subdirect product, as a regular submonoid of the semi-direct product of the monoid A and the image of the lambda map. The lambda map is exactly the action of the monoid M via automorphism on the monoid A. So in particular, the algebra of M sits inside the semigroup algebra of this semi-direct product. So applying this and knowing that the image of lambda is finite, in case our set is finite, and M is in bijection with elements of M are in bijection with elements of A, we get a formula for the GK dimension of Km. And using the above theorem, we know that GK dimension of Km is finite, provided our solution is finite. So if we come back to the theorem of Okniński, we see that one of the conditions is satisfied, right? So to deal with the Noetherianity of our algebra, we should know that our algebra, we should build a chain of ideas with the properties as in this theorem. And this is the most technical part of the proof, to build this chain. But before I proceed to that part, here is also an explanation that in the monoid M, so pulling some information about monoid A to monoid M, we obtain also that our monoid M satisfies ACC on right ideals because A has this property. And here we have a bijection between ideals, between right ideals of A and M. So the only missing part to describe Noetherianity is the construction of the chain with nice factors. And how we do that? So first, assuming that our set X on which our solution is defined is of cardinality n, we defined a set of ideals in the following way, that Mi consists exactly, we look at the relation of divisibility by generators, and Mi is exactly the set of elements in our monoid that are left divisible but by at least I generators. So we have a chain, but this chain is not enough because the factors are not enough good. And we put some intermediate ideals, and this is really a technical construction. Here is some information how to build such ideals. But I think I don't have enough time to explain the details. But the crucial part is that for arbitrary two subsets of X of the same cardinality, say I, we look at the elements of M written in that form, A comma lambda A, such that A is divisible precisely by generators from Y, and such that the corresponding permutation to this element A sets element from Z to Y. Okay? So since X is finite, we have finitely many sets Y and Z with size Y. So we have also finitely many corresponding sets MYZ. So having such a set, say fix Y of cardinality I, and if such MYY is a non-empty and semigroup, then there exists some special element in this semigroup which controls the behavior of these elements, and such semigroups controls the property of one-sided Noetherianity. And the proposition is as follows: that assuming that our solution is finite and one-sided left non-degenerate, say, then we have the following. If for each subset Y of X, such a subset of our monoid structure monoid MYY is a non-empty semigroup, and there exists D such that this special element, its D power times this semigroup, is a cancellative semigroup, then our structure algebra, our Yang-Baxter algebra, is right Noetherian. Maybe these conditions looks a bit technical because you have to deal with some subsets. And then you have to consider some semigroups of the structure monoid, but at least this condition is relatively easy to check because there are finitely many such semigroups, okay? Because they correspond to finite subset of X. So to check the Noetherianity, the problem of checking the Noetherianity is reduced to some finite problem. Moreover, the cancellativity of this semigroup holds in case in this semigroup multiplied by this d power of this special element, if there exists some case such that elements of this guy, k powers of elements in this guy commute, and if additionally M satisfy the ascending chain condition of left ideals, then our algebra is also left Noetherian. So we have a characterization of right Noetherianity, but not a characterization of left Noetherianity in terms of behavior of certain finite family of semigroups of the structure monoid. It can also be shown that the one-sided Noetherianity of the Yang-Baxter algebra of a solution is equivalent to Noetherianity of the semigroup algebra related to a bit smaller submonoid of M. This is the so-called socle. And the theorem reads as follows, that having a finite length non-degenerate solution, the corresponding Yang-Baxter algebra Km is right Noetherian if and only if the algebra of the socle monoid is right Noetherian, which is also equivalent that considering for each subset y of x, considering SYY, which is a subsemigroup of S, and D power should be a cancellative semigroup. So having such a situation, risk factors of these semigroups are not nil. So again, the conditions to check right Noetherianity at the level of algebra are reduced to check some finitely many conditions at the level of semigroups. Here I have some special what happens if we assume something more about our solution. For example, if it's finite and left non-degenerate, then, for example, if the derived structure algebra is right Noetherian, then so is also the structure algebra of the general solution of our original solution. And this happens, for example, if A satisfies the left ORE condition. For example, if A is Maltsev nilpotent, then the Yang-Baxter algebra is right Noetherian. Moreover, if A is abelian, in particular, abelian is a special instance of Maltsev nilpotency, then our Yang-Baxter algebra is also left Noetherian. And there are also special results concerning idempotent solution, but because I don't have a lot of time, I will skip them. So the conclusion is that right Noetherianity of such algebras, checking right Noetherianity can be completely reduced to checking some, to investigating certain finite family of subgroups, of subsemigroups of the structure monoid. And if they are cancellative, then we have to check some properties for these semigroups. And this completely solves the problem of Noetherianity. What happens for the primeness? And again, if we consider a finite left non-degenerate solution of the Yang-Baxter equation, then its Yang-Baxter algebra, its primeness of the Yang-Baxter corresponding Yang-Baxter algebra is in that situation is again, this problem is completely reduced to investigation of some finite semigroup, to the behavior of some finite group that sits in the structure group of the solution. And the result is as follows, that having finite left non-degenerate solution, the corresponding Yang-Baxter algebra is prime, and the group is trivial. This is equivalent that the Yang-Baxter algebra is a domain. This can be also expressed in terms of the monoid, that the monoid must be cancellative and this group omega must be trivial. And this is again equivalent that our solution is involutive. So there is some correspondence between combinatorial properties of the solution and algebraic properties of the algebra, right? Because the Yang-Baxter algebra is domain if and only if the solution is involutive, for example. So being a domain is a criterion for the involutiveness of the solution. Okay, there is also possible to find some conditions for semi-primeness. In that time, this time it's more involved, and maybe I think that 10 minutes. I just have 10 minutes, so I will skip some of these propositions.
Yes, I confirm. You still have 10 minutes.
Yes. So I just tell you that there is also a possibility to reduce the problem of semi-primeness of the Yang-Baxter algebras to certain properties of the monoids related to solutions, and these problems are again finitary in nature. The conditions you have to check are just finite. It's also possible to determine the exact formulas for dimensions of algebras that appear. And again, these formulas are determined these formulas can be expressed in terms of actions of certain groups on some sets. For example, if you look at this set curly Y, we consider subsets of X which are sigma invariant, and with the complement that is also sigma invariant. If having such a set Y, if you choose an element of this curly Y, then you have a monoid sigma Y, and this monoid naturally acts on the set Y. And if you count the number of orbits of this action, you get a particular number. But if you consider the maximum of such numbers when Y runs through the curly Y, then this is exactly the dimension of the Yang-Baxter algebra related to our solution. For example, the dimension is always bounded by the size of the set X. And using these formulas, using this description of the dimension, it's also possible to give some homological characterization of solutions in terms of properties of the corresponding Yang-Baxter algebras. And for example, we have the following characterization of the involutiveness. So having a finite left non-degenerate solution, this solution is involutive if and only if the GK dimension of the corresponding Yang-Baxter algebra is maximal possible. And this is also, there is also a bunch of other results which holds if we additionally assume that our algebra is left or right Noetherian, then conditions 1 and 2 are also equivalent, that the classical cool dimension is maximal possible, rank of the monoid is maximal possible. By rank, I mean the rank of a monoid. By rank of a monoid, I mean the maximum of ranks of three abelian submonoids of our monoid M. This is also equivalent that the injective dimension of the algebra is equal to the size of the set X. So the condition our solution is involutive is also equivalent that our algebra has finite global dimension, and this is also equivalent to some homological regularities of our algebra. And at the end, I will just mention that there are some results concerning degenerated solutions, that it's also possible that some classes of degenerated solutions lead to nice algebras, but unfortunately, we are still not able to find necessary and sufficient conditions. Here I have some properties about graded two-part, but because I don't have time, I will skip it. And at the end, I will post some open problems. So among the most important is that what is the sufficient condition for the structure algebra of a finite left non-degenerate algebra? What is the sufficient condition for such algebra to be left Noetherian? Because right Noetherianity we describe in terms of certain subsemigroups of the structure monoid, but we don't know what happens at the level of left Noetherianity. We know that in this case, left and right are not symmetric conditions. We also do not know what happens. We know that there exists some finite group omega that controls primeness of our algebra, but we don't know we don't know the exact description of this group. And the description of this group is crucial because it controls primeness. We also don't know exactly, we have some necessary conditions for semi-primeness, but we don't know the sufficient conditions for primeness. And this is again important because knowing that we deal with a solution such that the corresponding algebra is semi-prime, we previously proved that our algebra has a faithful representation in a finite product of matrices with coefficients in group algebras, and these groups are very nice. They can be built as cancellative as group of fractions of certain cancellative subsemigroups of the structure monoid, and these groups also have some nice extra properties. So knowing the necessary and sufficient conditions for semi-primeness allow us to find faithful representations in finite matrices. And we don't also know what happens with, for example, with Noetherianity for degenerated solutions. So somehow this is a work in progress. And this is more or less all what I wanted to say. Thank you.
Okay. Thanks, Lucas, for this interesting talk. Are there any questions?
You should, yes.
Questions, comments, or remarks? I don't see any question. So in this case, let's thank the speaker again.
Thank you.
And we will resume on next Monday at the usual time. Thank you. Bye.
Bye-bye.